Hello everyone. So in the previous sessions, we started our discussions with KNN and we tried to introduce different concepts of machine learning and deep learning through that KNN. And we were discussing the topic of underfitting and overfitting. Actually, the topic was how to set the hyperparameter, how to set the hyperparameter K. Just a bit of revision. So in KNN, the point was like we just found the k nearest neighbors, and then we did a majority vote to find which are the labels it's in majority, and then gave the majority label to the query point. So that was that was in short what KNN means. So in that we have to set this k. So this k is a hyperparameter. Is there a question? Okay, so this KNN, we had this k as a hyperparameter. That means we had to set it. So I said how to set it. So we tried with a different approach, and then I said something about overfitting and underfitting. This is the topic that we are discussing: overfitting and underfitting. So what is the meaning of overfitting? I also touched upon this because we'll be looking at this overfitting and underfitting terms in different perspectives. So whenever there is a model which tries to capture everything, so if I had to write about overfitting, so overfitting means when a model tries to capture even the noise. So it works really hard to get everything right. So that's what I mean by overfitting. So overfitting occurs when a model is too complex. So when a model is too complex and tries to even capture everything and tries to capture everything. Everything means it also captures some relations and also captures noise. So it tries really hard to get everything right. So I said, for example, if we had data points like this, if this was, let's suppose, bunch of points we had, then if we had these blue points, let's suppose there was some misclassification over here, and there is some misclassification. I mean, ideally should happen. So how the decision surface will be drawn? So it will be like this. It will try really hard to get these points also right. So that's the meaning of overfitting. But you can see that these points are clearly like the outliers. So it does not generalize well. So I'm saying this: overfitting means when a model is too complex and learns to capture the noise or the random fluctuations in training data, rather than underlying relationships between the features. So that is why overfitting happens. So we'll see different perspectives of these, and then we also saw what is the meaning of underfitting. So underfitting means when the model is too simple. When the model is too simple. So in here, when you try to capture, for example, if I just copy these data points, so I'll just paste them here over here. So what's the meaning of that? It won't do anything. So for example, I said in that we said underfit if k is equal to n. If k is equal to number of points, let's suppose we have n number of points. So there will be two classes. One will be minority class and a majority class. So let's suppose n1 are the points which are from class 1 and n2 are from class 0. Let's call these classes this class 1 and class 0. So if I say that n1 is greater than n2, that means the number of points in class 1 are greater than class 2. Then we'll say class 1 is majority class. Then we'll call this a majority class. So I said when the underfitting happens, so the whole classifier will be biased towards the majority class in KNN, if you see that. So what KNN does, it will check the k nearest neighbor. So now the k nearest neighbor, if I have a query point, for example, right here, ideally it should be given the red class. So but what will happen is it will not just create, it will not just have capture the distance between some points, it will compute the distance between all the points and do a majority vote. When it does the majority vote, obviously the majority class will win. So for example, the majority class here is red, so it will be red. So even if you have a query point over here, ideally it should be in the blue class. But what will happen is, so it will compute the k nearest neighbors, that is n nearest neighbors in this case, and it will give the label as majority class. So here it will basically underfitted. So what's the meaning of underfitting? Model is too simple and it does not capture any relationships. Okay, here an overfitting model is trying too hard. It's trying very hard to get everything right. In underfitting, it does not care. Okay, that's what I told you about underfitting and overfitting. The point was we're trying to see what to do about this overfitting underfitting, how to basically overcome this problem of overfitting underfitting. So we should get what is known as best fit. Best fit. Now we saw that this k, if we set it in certain way, we can underfit or overfit the model. So the topic was how to set the hyperparameter. So when we saw that if we set hyperparameter in a certain way, we can get underfitting or overfitting. Now we need to find a best fit. So best fit will do that with the help of k. Okay, so that's a hyperparameter. How do we find best fit with respect to so for example, if you have learning parameters, that will happen already there, but k also you have to find an optimal value for k so that you get the best fit. So that's what I mean. Now we have to avoid this overfitting and underfitting. So how to avoid this? So we can also call it finding the best fit. Let me write it. So finding the best fit, or avoiding this, avoiding underfitting slash overfitting or overfitting. Okay, this is the thing that we want to see. We want to avoid this. We want to see like how can we find the best fit, and we so that we can avoid overfitting. There are a lot of techniques to do this. Okay, so there are techniques like you'll have to do cross validation. Like I'll just mention the techniques, and then slowly and slowly once we progress in the course, so you will almost learn about all the techniques. So once the topic is there, then we'll sort of have a detailed discussion on that. So the first thing is cross validation. Cross validation. And then other techniques are regularization. Regularization. Other technique, feature selection. Okay, then we have something called early stopping. There are a lot more. Okay, but here we'll discuss about this. I think I started the discussion over the cross validation also. So this is the topic of our interest today. So we'll be learning about cross validation. So again, have the bigger picture. So we wanted to set the hyperparameter, but now we saw that when we set the hyperparameter, we can overfit or underfit the model. So we need to find the best fit. Now, in order to avoid that best fit, or in order to find the best, in order to avoid this underfitting and overfitting, or in order to find the best fit, so there are different methods we can use. The first method that we are going to use is cross validation. So let's first see how did we split. So I said there's a problem of generalization. So if you remember, I said generalization. I asked you a really good question. I said, for example, let's suppose I have this data. Let's suppose this is my data. This is the n, the whole data set I had. So usually what we do is we'll split this data into dtrain and dtest. Okay, so what we do is then we'll use this dtrain to train the model. So whatever model we are using in this particular case, we are using knn. So we'll use this trained data, and then after the model is trained, then we'll use this test data to compute whatever the metric, whatever the evaluation metric we have, accuracy, maybe f1 score, whatever that is. We'll see that, and then we'll use test data. So I was telling you, for example, in knn what we usually do is in knn, so we use this data set. So in the knn, if we have this dtrain and the dtest, so we'll use this dtrain to compute the nearest neighbors, and we'll use this dtest to compute that k. So how was k computed? So what we try to do is, so let me just draw a thing like this. So we'll have this dtrain data. Dtrain data we have by the help of which we can compute the neighbors. So we'll have the value of k. If k is 1, so what we'll do is from the test data, we'll take each point. We'll take each the point from test data, and then for each point in test data, we'll compute the distance of this distance of the neighbors, like first neighbor from this dtrain, and then we'll compute the accuracy. So we'll compute the accuracy with respect to 1k. So 1k means just check the topmost least 1k distance in the training set. So for example, let's suppose we got the accuracy of 0.7, then we'll just change the k. We'll say 2 neighbors now. So take each point of from the test set, and then compute the accuracy with respect to 2nn. So just compute the 2 neighbors and see if the labels given are correct. Let's suppose this is now say 0.6, and then 3 neighbors. Let's suppose this is 0.65. 4 neighbors. This is, let's suppose, 0.8 or something like this. So then we'll just vary this k from, let's suppose, 1 to 20, and we'll see what is the best accuracy value that we'll get. Let's suppose on this 4 value we got the best accuracy on this 4 value. Okay, so now we got the accuracy of 80% over this. So when we had k is equal to 4, we got 80% accuracy. But what did we use? We used this d test to set this k. So I asked you a question. Can I claim that this 80% accuracy is on unseen data? Can I say this? Again, I'm asking you the same question. Can I say this?
No, sir.
No or yes? I didn't hear you clearly.
Yes, sir.
You said yes. So in the previous
No,
session
no, sir.
also, I said like this should not, because this remained no longer unseen. Because the problem now had, we use this test data to set the parameter k. Okay, I can say that this 80% is the accuracy on test data. Okay, unseen means model should not see it any so way. Okay, that is what I meant by generalization. Generalization means it has an assumption that whenever you deploy this model or use in the real world, it should perform good on the real world sense, and it should perform good on the unseen data which it was not trained on, which it was not, like, any data was basically not used anywhere. So that's what I say in the spam filter. Let's suppose we were discussing the spam and not spam example. So in this I said, if I have emails, so in the emails I have bunch of emails. I saw a bunch of emails. I trained on these bunch of emails, and then what I did is I used this test emails to set this have parameter k. If I got the test accuracy 80%, that doesn't mean that I got the generalization accuracy of 80%. Okay, by generalization I mean that when there is an unseen data, okay, I should get the accuracy on that thing. For example, if I trained this and now I got d test as 80%. Now if I tested it in real world, for example, I tested it for, let's suppose, 100 days, and then I'll see how many spam and non-spam emails did it correctly classify. That will be my generalization accuracy. Okay, is it clear?
Yes, sir.
So in order to
Yes, sir.
avoid this, we had this cross validation. So that's why we brought cross validation into picture. So how many of you understood what is the need of cross validation? So if you only split the data into train and test, so maybe you can use, sometimes in some algorithms you can use this test data to set some parameters or do something. So that is also then our model is biased towards the test. For example, you change have parameters based on what test accuracy get. Usually you will do this. So what you will do is you are training the model. You train the model, and after that you are using the test data set. So this is our d train. So this is our model, let's suppose. So you are training it on d test and d train, sorry. So you are training it on d train, and then model has some it learns some parameters. Okay, or you set some have parameters also. So then you will use this d test, okay, to find the accuracy. Let's suppose your accuracy is say 80%. Now there are two types of approaches. Okay, one is called as the model centric approach. Okay, one is called as model centric approach, and second is called data centric approach. In order to make your model better, and in order to make a good model, so here you can change the model itself. For example, you're using k and you'll use some other model in order to test it. Otherwise, what you can tweak the model. Okay, you can tweak the parameters of the model. So this is basically you are tweaking with the model so as to get the better accuracy. Okay, in the data centric approaches, you again look at the data and you see if there is something missing in the data, and if there is something which I can clean the data as well, and then I can do something to get the better accuracy. Sometimes, like, both of these are good. Sometimes people use this if they are confident about their model. This model is good, and they look at the data again. Why is it performing so badly? Okay, so usually what we are dealing here is this model centric approach. I'm telling you that we train the model on D-train, and then we test it. We got 80% accuracy. Okay, then we are setting the HAP parameter again. We are saying no, something is wrong. Let me set this HAP parameter again. So I set the HAP parameter. So what I'll do is I'll again test with the data set. So now I got 85% accuracy. I said no, this is not even good. So I again will tweak something. So I again tweak the HAP parameter. Now I got 90% accuracy. Okay, because this accuracy was increased when I was testing it. So this data set now no longer remain agnostic. Okay, this is some sort of the thing where we use this data set to set the parameter to tweak the model. So if we got accuracy of 90%, we can say that we got test accuracy of 90%. We cannot say that we got the generalization accuracy of 90%. That is that it will perform 90% accurate on the future data. That is where this concept of cross validation came in. We want to make sure that we can say that the accuracy that we are now getting is on the unseen data. That's the need of cross validation. So in this, what we do is, so in cross validation, now we'll not just divide data set into two sets. We'll divide data set rather into three sets. So we have this dn. So we'll have d train, then we'll have d cross validation, and then we'll have d test. Okay. Now we'll sort of divide this into these three things. We have this d train, we have this d test, and we have this d cross validation. So in this, what will we do now? In this cross validation, what we'll do? So now if you see the data set, let's suppose this was our data set. Now d train is, let's suppose, 60% of the data. D validation, let's suppose, is or 20%, and D test is or 20%. Okay. We'll keep this D test as completely unseen. This is complete unseen. Okay. We will not do anything with it. It's as just, it is like, for example, we did not have this data at all. We'll just work with these two data. So what we'll be doing is, so we'll first train the model on this D train, and then we'll test the accuracy on this test, on this validation. So we'll train the model on this D-train and then test the model on this validation set. So if we got an accuracy of, let's suppose, 60%, then we'll tweak the model. We'll set the hub parameter. In our case of KNN, we'll set the hub parameter to, let's suppose, k is equal to 1 to, and we'll vary this hub parameter. So we'll get the accuracy, let's suppose, in the second case, we'll get 70% of accuracy. Okay. So if we get the 70% accuracy, so we again want some more accuracy. So that will again tweak the model. So using the train, then again tweak the model, testing it with the cross validation, and we'll get the accuracy of, let's suppose, 80%. Now I have these accuracy. I got 80% accuracy. I'm confident that my model is performing good. Now, in order to further test, in order to test it on unseen data, because the test data was not shown to the model. So what I'll do is, I'll take this test data. Now I'll test it. I'll test the model, whatever I have parameters I chose. So in terms of KNN, I used this train data to compute the nearest neighbors. I use this validation to compute the k. Okay, then I use this for testing purposes. Okay. And when I set this k, and when I use this train data to compute n, and then if I get the accuracy on of this testing accuracy, now I got, for example, 90%. Let's suppose. Now I can see that on the unseen data, this model gave an accuracy of 90%, because the model never saw this data even. So even when we are setting the hub parameters, when we're training the model never saw this data. So this is what is mean. This is the meaning of generalization accuracy. Generalization accuracy. Many of people I have seen, many of people do this. So they'll just split into train and test, and they'll train the model and then tweak the model again, see the test accuracy, then they'll claim this is the test accuracy, because they're continuously updating their model based on what the test accuracy they are getting. So it is really important that you have this validation set, so that the accuracy you are claiming is not the accuracy on test only. It should be the accuracy on the unseen data, basically generalization accuracy. Is it clear? Let me show you the code where we'll see like how to set this k based on these different things. So first, how do we set k? It was based on the test set only. Okay. So if you see these lines of code, so here we have this x train, x test, and we have just subsetted the data into two classes. That is x train. So we had this data x, and we have two subsets now. We have this x train. Okay. So we have this x train, and then we have x test. So these are the two things that if you can see over here. This is x train and this is x test. So there is a library called as scikit-learn, from which I imported this test turn split. Okay. And now what I'll do is, based on this this train, because I'll train the algorithm on this train. For this, on this x test, for each point I'll compute the neighbors. Now I'll vary the k. So what I'll do is, I'll vary the k from 1 to 10. So here if you see, I'll vary that k from 1 to 10. I have varied it. So now what I'm doing is, first I'm calling this KNN to compute this, and then I'm training the model, if you see it over here. But this is for k is equal for k in k values. That is, I have this value of 1 to 10. Basically, it will take 1 to up to 9 values. So then I'll plot this. I'll compute the accuracy with respect to each of these k's. So if you see, I am computing accuracy score, and then I'm appending it to this accuracy list. If you see it over here, so for each of the k, I'm appending this accuracy. Then I'm using this accuracy list, and then k values of k, and then plotting it. Okay. If you see the plot over here, so this is the plot. Okay. Let me Just run the whole notebook once. Okay. So this is the graph if you see it over here. So now if you see on this, on k is equal 4, on k is equal 4, we got the maximum accuracy. Okay, we got the accuracy of like 0.98. That's why I use this k. But now the claim, the accuracy that I have, this 0.98, this accuracy, I cannot claim this accuracy to be the generalized accuracy. I can call it test accuracy only, and this is not on the unseen data because I have set this k by using the test data. Okay, is it clear? That's what I was telling you in the theory. Now here I showed you it graphically also. Is it clear?
Yes, sir.
Okay, now in the second case, what will we do is, again in the second case, going back, so we'll train the model on this. We'll set the parameter k by using the validation set, and then we'll use this test accuracy. Okay, then we'll use this test part, and we'll claim this. If we got some accuracy, we'll say this is the generalization accuracy. Okay, let me again go back to the code window to show you that. So here is it. So now what I am doing is, I'm again having these k values. If you see it over here, I'm having these k values from 1 to 10. Okay, I think now I haven't wrote the separate code for that. So here now you see, if you see this, now we have this x train, x test, and then with this, if you see, we have again a validation set over here. We have this validation. Okay, we actually broke that. We had the whole data like this. So this was our dn. So first we broke up into d train, and then we had d test. So we kept the d test as it is. Okay, then we broke this d train into d cross validation again. That's what is happening here. So first we had this x train, x test. This was the split on the actual data, that x and y. Then what we did is we took this x train, if you see this x train over here. So we split again into x train and x validation. So now I have these three sets. Now based on these, what I'll do is, the first thing is I'll compute the accuracy on this validation set. Okay, this validation set, I'll compute the accuracy, and then I'll set the HAP parameter based on this. And after I'm done with finding the HAP parameter, let's suppose I found some k, and then I'll test the accuracy. That's what I'm doing here. So I'm ranging the values of k from 1 to 10. So I'm ranging from 1 to 1 up till 9. So what I'm doing is I'm computing the accuracy. If you see over here, I'm computing this with respect to validation set. Okay. So and then I'm seeing which is the like where did I get maximum accuracy. I'm setting that k as best k. That's why I'm setting best k is equal to k values np argmax. That means wherever I got the maximum value of accuracy, that is my k value, and then I'm plotting it. If I show you the plot now, so this is how plot looks. Okay, you see that it somehow got stabilized at 2 3 because it's, I think, getting 99 accuracy, and then it suddenly dropped when I increased it. So that's what I'm here. I'm showing this. The best value for k on the validation set data is 2. Okay, I can set it at 2 3 or something. This is based on it because it's a random data. But now the accuracy achieved at k is equal to is 0.99. So now can I claim for this 0.99 that this accuracy is the generalization accuracy? Can I say this?
Yes, sir.
Yes. Why can I say this? Because I haven't used this data set neither to set the parameter, neither to train the model. It was completely unseen for the model. Okay, I use cross validation set so that I can set the hyperparameter k, and I use train data set so that I can compute those nearest neighbors. I have nowhere used my test data set while I was training and validating whatever I did. So in the testing, so this purely was unseen data. That's now I can claim the generalization accuracy of this model is, let's suppose, 99% when the k is equal to, and I found this k is equal to by using the cross validation set. Okay, am I clear?
Yes, sir.
Now, do you see
Yes,
any
sir.
problem with this? Do you see any problem with cross validation? I'll tell you one problem that I see with cross validation. I think this problem should be like easy enough to find. Please put
Sir, it
yourself on the
makes the test data,
no, no, no. Okay, come up again.
sir, because like we use cross validation for verifying
Mm-hmm.
like the test data. That's why like the test data becomes like the trained data, I think.
No, no, no. Actually, that's not the problem with, because the test data is completely unseen now. The problem that you see over here is, if you see it like this, so we had 60% of training, 20% of validation, and 20% of testing data. So now you see we only use 60% for training. So in machine learning, there is generally an assumption that whenever you have more data, the model performs better. Okay, now we are sort of losing 20% of data in from this train. Initially, we were training the model and we were learning the parameters, whatever the model you were using, let's suppose linear regression or KNN, we were learning the parameters based on the trained data. Okay, now we have only 60% of data less. So the assumption is that more the training data, more will be accuracy. More the training data, more is the accuracy of model. That's the usual assumption. Okay. Okay. So what I'm saying is, if you have data, try to have more data, because whenever you have more data, you capture a lot of variation. Okay, when you capture a lot of variation, then your model performs better. For example, if you have, let's suppose, 1,000 people, 1,000 people, if you want to make a phrase recognition system, so different 1,000 people will look. There will be a variety of people. Some people will have different complexions and they'll have different ethnicities and things like that. So based on these facial features, we'll train a model. Our model will perform better if we have 1,500 people, if we have more variety of the data. Okay, so that's the assumption. What I'm saying you is that more the training data we have, more will be the accuracy. Okay, so here if you see, we are losing this 20% of the data because we are not using anywhere it in the training phase. We are just using it to set the hub parameters. Okay, in order to mitigate this problem, in order to overcome this problem, there is something called as k-fold cross validation. I hope that you got the problem. What is the problem with the this cross validation? Because now we are losing some data, so I don't want to do that. I actually want to use all of my data, and for that purposes, we have this k-fold cross validation. Okay. Now I'll show you how do we split this data into this, and then I'll slowly go step by step. Please, this is a really important concept. If you do not understand a thing, just stop me right there and then ask me questions related to this. So now I'll show you what this is a widely used technique for model evaluation and validation. Okay. So now I'll show you the working of this. First step is how do we split data? Splitting of data. Splitting of data. How do we split the data now? Actually, you know that we had this DN. How do we split? The data set is actually divided into k subsets or k folds, I'll call them. Okay, of approximately the equal size. Okay. So if you have this, now whole the data we have nothing to do with the test now. So we have this data. It is first divided into D train and D test. This is our D train. This is our D test. So initially what we did, so this is unseen for us. So this part was total unseen. So we did not see it for any purposes because we want to keep unseen. So we will compute the accuracy. So now in just cross validation, we divided this and we took a chunk of this data train so that we make it a cross validation data. Now what we'll do is we'll equally divide this D train. Okay. Let's suppose these are k folds. Each of them is called one fold. Here we'll have this data, for example, first fold, second fold, third fold, fourth, fifth, and sixth fold, something like this. Okay, let's call this let's take an example of four-fold cross validation. So from on that, I'll just divide this D train into four folds. I'll say one fold, second fold, third, and fourth. So this will be called as D1, D2, D3, and D4. Now I have four-fold cross validation. This k is different from the kn's k because both of these are variables, so we kept it k cross validation. Okay, so here that k is the hab parameter, the number of neighbors, and this k is the number of folds you are going to use. Now we split the data in this way. So we had this whole data set, we call it dn. So first we split into d train and d test. D test was kept separately because that is the unseen data we want, and where we are evaluating the model finally. For this D train, what we did is we divided the whole D train into four folds, and each fold is approximately of same length. You can even have the unequal sizes, but usually this is the rule of thumb that we usually divide these k subsets approximately of equal size. Okay. Now in the each iteration, what we do is we repeat this process basically k. We repeat the process k times. So what I'll do is for k is equal to 1, I'll say for k is equal to 1, the first thing is I'll use the training and the validation. Okay, for training I'll first use d1, d2, and d3. Okay, and I'll use d4 as validation. Similarly, and again when k is equal to 1, so I'll use d1, d2, and d4 as training, and then I'll use D3 as validation, and parallelly I'll compute the accuracies. With respect to this D4, D3. Okay, and then I'll use now D2, D3, and D4. So here D1 will be the validation set. Again with the one I'll have the D2, maybe let's suppose what I missed, D2 here. So D2 I'll not keep it. I'll say D3, D4, and D1. Okay, I think I just took k minus 1 for the train and k for the validation. Now I'll have accuracy A4 accuracy, I'll have A3 accuracy, A1 and A2 accuracy. So what I'll do is I'll now compute the average of these accuracies. Let's call that capital A accuracy with respect to k and 1. I'll call it A1. Then what I'll do is for k2, now I'll say k2 with the k with two neighbors. Again I'll use the same set. I'll use all of these. Similar, they'll be repeated. So I'll copy it, again paste it. Okay, here we'll hand out 2 NN, two neighbors. So again I'll get some accuracy. Let's call this A4 dash, A3 dash, A1 dash, and A2 dash, some accuracy, and I'll average it out. I'll compute the average of all of these. I'll call it A2. A2 means average accuracy, and I'll do it for all the neighbors. So this process will be done for, if we have k ranging from 1 to 10, so this will be repeated 10 times, the whole process. First we'll repeat these many times, okay, and then we'll within each iteration we're repeating it 4 times everywhere if it's a 4 cross validation. And for this k, if it ranges from 1 to 10, and we'll uh, reiterate the process 10 times, and then we'll see which of them gave the good accuracy, which case now gave the good accuracy. Now if you see that each of the data set, each of these data folds, this D1, D2, D3, D4, they were used in training as well as testing. So they were used in training as well as in validation, basically the testing thing. Okay, so in order to set that k hub parameter, and after that, after we compute these accuracies, A1 average accuracy of this, average accuracy A2 with respect to K2, and then we'll say which of these models is better. And at the end what we'll do is, if let's suppose we found k is equal to 4 to be the optimal k where we got the maximum accuracy, so for that, then what we'll do is we'll bring the d test, and finally we'll test the model. Is this clear? Is this k fold cross validation clear?
Yes, sir.
Okay, so I just again reiterated the data. So first we have split the data. How do we split it? We'll split it into D train and D test, and then D test is complete unseen for us. We don't look at it. And then for this D train, we'll split it into equal folds. This can be k folds. Here we said these are 4 folds. Then for each of the fold, for each of these fold, we'll use it k minus 1 times in the train and 1 times in the validation. So it is here used as validation 1 time, and then it is used, if you see this D4, D4 is used in training, and k minus 1. So I can write it here. Every fold is used in training how many times? K minus 1 times. K minus 1 times. And each fold is used in validation how many times? 1 time. Okay? So this whole of this process is repeated k times. So if you see, I repeated this process for k is equal to 1. Then I repeat it for k is equal to 2. I will repeat it k times because we are doing knn. Okay, if you see it over here. So that's why this whole process will be repeated k times. Then we'll see where is accuracy, or we'll compute the error, and then we'll basically see where we got the maximum accuracy, and that will be our k. And at the end we have this d test, which was completely unseen. Then we'll evaluate our model based on that. Is it clear?
Yes, sir.
If it is clear,
Yes,
let
sir.
me show it in the code, and I'll sort of give you a walkthrough through the code. Okay, so we have data defined, and I'll sort of describe this from here. So you know the k values now are from ranging from 1 to 10. So we'll say k is equal to 1, k is equal to everything like that. And then we'll have number of folds is equal to 4. Okay, number of folds here is 4. We're using 4 fold cross validation. Then we're initializing a list of average accuracies, because you know that for each k we'll compute average accuracy. Okay, let's go from here. Let's see the internal, what will it do. First I'm defining the fold size. Okay, so what I'll do is I'll compute the whole length divided by number of folds, and so that it will equally divide the folds into these number of data points. So in our case, for let's suppose if we have 100 data points, so if we have 4 folds, so each fold will have 100 divided by 4, that is equal to 25 points. That's what I'm computing over here. If you see fold size, that's length of data, that's 100 divided by number of folds. So number of folds, if we see, is 4. So each of these fold size will be 25. That's what I'm computing for. Fold size I computed. Then I'm saying indices. So indices basically means from where to where I'll compute it. So I'll getting the indices from NP range, and this will be length of basically this will give me a number of indices, total indices. Okay, 1, 2, 3 up till 100. If you know that what is the function of NP a range. So if I write NP a range of 10, so what will it give me? It will give me a list of numbers which will be from 1 to 10. Okay, so this is what it will give me indices. Basically 1, 2, 3 up till 9, it will give me these number of indices. Then I am computing validation indices. Okay, so for each now, because I have to use each time I have to use a different validation set. That's why I am using this I. If you see, I am saying I multiplied by fold size from this. For example, first if you see the first fold, now we have this fold. Now we got the indices. Let's suppose from 1 to let's say 100. So if this is our train, let's suppose we have test data separately. Then what will it do is for the first iteration, because the value is 0, it will say I multiplied by fold size, that is 0. So it will take fold of 0 is 2. Then it will say I plus 1 into fold size. I plus 1 is 1. So 1 fold size, that means because fold size we know is 25. Okay, so it will say the first fold is 0 to 25. This is the fold 1. Okay, that basically should this is fold 1. In the second iteration, what will happen is it will take the second fold. So this is our 4 folds. The first fold should be from 0 to 24. Then it should be from 24 to I think 49, 49 to 74, then to 99. Okay, these are our folds. This is how it computes. So this line, if you see it over here, so this line computes this indices line. It computes the fold size. In the second iteration, what will it do? It will use the validation. It will do fold, because now we have I is equal to 1. You see, it's I multiplied by 25. So it will start with 25 index. Okay, then where will it go to? It will go to 50. 50. Okay, so basically it will capture this much. Second fold is this. Okay, third time it will basically do this fold. That's what this code is doing. Okay, and train indices is whatever is left. That's why it's saying like indices from this to this and leave the other part, and whatever the validation was, just have rest of the train indices. Now we have this x train, x train fold, x validation fold, and we have this y train and y validation fold. That's how we basically have these folds. Is this code clear? I think it should be pretty clear by now. Is it clear?
Yes, sir.
Then for each of these, when we have this, for like, let's suppose we have this d1, d2, d3, d3 and d4. Now we use this as validation. Let's call this as validation, and then these as train. This was our d train, and this was our validation, d validation. Okay, now we'll fit the model. If you see, we fitted the model over here. Then we made the prediction on this x validation. We made this prediction on x validation because we have to set k based on that. Okay, now this will basically happen how many number of times? For example, in here it will depend on what's the number of folds. It will happen 4 times. So we'll have this fold accuracy is continuous, and we'll append this into this fold accuracy is append dot fold accuracy, because we are adding that into this. And at the end, if you see, we are computing the mean. We are computing the mean through each iteration. Then that mean is basically appended into this. And for example, that's what I showed you over here. So if I just close the code window for a second. So what I showed you here is, so this thing will happen continuously. So we are adding this A4, A3, A2, A1 to that list. And then at the end, we're taking the average. That's what I was doing there. So just going back to the coding window, if you see, that's what I'm doing over here. So first thing is I'm computing all the things and I'm adding that into fold accuracy. I'm adding that A3, A2, A1 into this. At the end, I'm taking the average of this. That's why average accuracy NP dot mean of fold accuracy, NP dot mean of this. And I'm also appending that mean now, whatever mean I got, whatever this average accuracy I got, I'm adding that into this average accuracy. And that's what I added over here. So when I added this, I'll repeat this process for k is equal to 1, k is equal to, that's what outer loop is for. Outer loop basically ranges from 1 to 10. So it's for these values, k is equal to 1, 2, 3, 4 up till 9. And the inner loop is for the folds. It will just compute the first A3, A2, A4 and then average them out. Okay, then based on these folds, we'll get where did we get the maximum accuracy. Okay, and we'll plot that and we'll see what that is. If this is clear, let me show you the graph. Okay, so this is the graph. Now if you see that here, this is the graph, and you saw that in one we had pretty much this. Let me just erase this much. So here we have the accuracy at k is equal to 93%, then at k is equal to 5 we have some higher number than 93. Okay, so now we will select this because you saw maximum accuracy we got is at here, at here, and here. Now the least number of k that I can use is 5. So that's why I can say this. The test value of k using k cross correlation is 5. So when I use the k cross validation, so I got the k is equal to 5. Now this test accuracy, this actual test accuracy, because we have d test as separately. So d test was now used in order to compute the actual generalization accuracy. That came out to be 96. Is it clear? Is the k cross validation clear? K-fold cross
Yes, sir.
validation. Is the
Yes,
code
sir.
clear?
Yeah.
Okay, that's the importance of this, because you have to get the real accuracy. The whole point is how good you generalize, how well you generalize. Okay, that's the point. We want to generalize it really well. If you do not generalize it well, then there is no point of having a model. For example, you get really good accuracy on, let's suppose, the data it saw, and it's basically doing the memorization. It's just memorizing the whole data set. As I said, you like different times that some people claimed that we had made a really good spam filter, but what they actually did is whole the test data was there in training. So whenever they were testing it on training, actually that was there. It was memorizing the whole data set. That's why we use this k-fold cross validation in order to make sure that we don't use this test data anywhere in the model training and in the model validation. Now, what's the problem with this? What's the problem with k-fold cross validation? The one problem is that it's really time consuming. Okay, it takes a lot of time, hell lot of time. So if you see how many times it was like running two loops, a loop within a loop. So that's one of the disadvantages. So I can write the advantages first. So advantages are, okay. So it utilizes all the available data. That is the first problem that we had with only cross validation. So it utilizes all the available data. Okay, that's it. Maximally utilize the data. Second point is it provides a more reliable estimate. Okay, this is more reliable estimate because now you are trying all the possible combinations. Okay, it provides a more reliable estimate of the model, because now you can say that this is the generalized accuracy because you have used the data everywhere, and then you have tested it on the d test, which is properly unseen data. Okay, so where is again useful? It is useful when we have very less data. Okay, it is useful when we have less data. Okay, so if you let's suppose I have only 300 points and you want to maximally use those 300 points, you cannot only use like 60% for the train, 20% for let's suppose validation, and 20% for the test data, and you cannot afford that. Even I had an example. Amir asked me a question for can I remove the data? The problem with that is, let's suppose sometimes you are testing a patient and the test costs you $2,000 or something. I give an example. I said if you only have now, let's suppose, 10 patients, you cannot afford to just miss out a patient. So here you can use the k-fold cross validation. Okay, these are the advantages that it gives. What are the disadvantages? So I'll write the disadvantage in red. I hope that you are making really good notes. Even I suggested you to make blog out of these, so it'll be really good for you if you make blogs. The first thing is it is computationally heavy. It takes a lot of computational resource. If you saw in the code, even it used loop within a loop, for loop. For example, if we are using k times, we're running the outer loop, and inner loop we're running, for example, for a number of fold times. Let's call that k dash. So it is k multiplied by k times the complexity of that thing. So it's a really huge number. So let's suppose if we ran from k is equal to 1 to 1000 and k dash, let's suppose we had 100 fold, so it will be easily 100 square. Okay, so that's what I'm saying. It's computationally really heavy. And second disadvantage it is that it is not suitable for time series data. Okay, so it is not suitable for time series. So I will get to time series, but just remember this point that it is not suitable for time series data because they have temporal dependencies. What is time series? I think I have told you somewhere that there is a temporal component. In stock market, if you see that the price sort of varies with respect to time. Weather data, if you see weather varies with respect to time, that's these data are called time series data where there are a temporal component. Okay, so it is not suitable for time series. When we'll go to the time series, we'll see why it's not suitable. Okay, is this clear? Is it
Yes,
clear?
sir.
Yes,
Nice.
sir.
Now we have the problem. Now we have the problem that if we now know everything, now we have this cross validation, we have everything. So how to sort of know that we are not underfitting or overfitting? Now we are trying to answer the question. The question was, where can I say am I underfitting? Where can I say am I overfitting? Okay, that is the question I'll answer now. When I'll know that underfitting is happening or overfitting is not happening. Okay, so now I'll answer that question, because now we have all the background to understand that overfitting and overfitting versus underfitting to find the best fit. Okay, so now if you see the graph, so what will happen is, okay, if we have this graph, so now we'll say we have two terms. Now first, before understanding the graph, you know what accuracy means. Okay, and 1 minus accuracy is error. We have also seen that when we read about the loss functions. I said that 0 1 loss means basically the error. So that is that error. Accuracy is whatever the loss we had, and just subtract it to that. So that's what I said. So accuracy, if for example, is 98%, that means error is 2%. Okay, if accuracy is, let's suppose, 0.98, so error is 1 minus of accuracy, that is 0.02. Okay, so this is the error. So in order to see which model to take, which k to use, now you know that there are different types of errors. So let me just define some types of errors. So you know error now is 1 minus accuracy. Accuracy is the number of right predictions divided by total predictions it made. Okay, so I'll first formally write it. Accuracy is number of right predictions divided by total number of predictions. This is accuracy. And what is error? So error is 1 minus accuracy that we saw previously. So now there are different types of errors, different types of accuracy. So first accuracy, I'll say this is called as training accuracy. Training accuracy. So what is the meaning of training accuracy? Let's suppose you trained the model. Now model learned something. If model learned something, now you are using training data, detrained data, and seeing how much accurate model is with respect to this data. So what accuracy you are getting that time, that I'll call as training accuracy. Okay, training accuracy is whenever you are training the model and then you use the same data, trained data, and then you test it on the same data, you see, evaluate the model. Okay, whatever accuracy you get on the trained data, we call that training accuracy. Then we have something called as validation accuracy. So validation accuracy is the accuracy that you got on the validation set. So we had that cross validation set. So whatever accuracy you got on that, that's called as validation accuracy or validation error. Parallelly, we have the similar terminology for this: training accuracy or training error, validation accuracy or validation error. Similarly, we'll have this testing accuracy or testing error, testing accuracy or testing error. So when we use the model, when we use the whole test data and we test it and we evaluate the model and get some error accuracy based on that. If I now make this graph, this is the graph. So for first, if I see if k is equal to 1, you know that everything in the train will be right. Okay, so the graph, for example, if this is 1, this is 2, this is 3, this is basically k. I'm saying this is the value of k. So you know it will be sort of 100%. There will be zero error. So if this is error over here. So if you see this graph, the more you increase this, so it will keep on going back to the error, and sometimes it will just decrease and do something like this. Because what will happen is at k is equal to 1, it will be perfect. Because that's what I showed you over here. If I just paste that diagram, so if k is equal to, oh no. So if I have this data, so if I have my data like this, okay, so if I have, this is the training data I had. Let's suppose I had some mistake over here, and I had some, I'll say abnormal point here. So if k is equal to 1, how is the graph made? So the graph made is like this. So it'll try really hard. It'll try really hard to get these right. Okay, that's why the accuracy will be 0 on training. Okay, so that's what I'm showing it over here. So graph will look something like this. Okay, so it'll keep on going like this. Mostly at 1, when k is equal to 1, the graph it'll give the 0 accuracy. And if you see it, so if I take a big picture, so it'll be like something like this. Okay, it'll keep on. So once you keep on increasing k, the training accuracy, this is training error, this is retrain, training error. So training error will keep on increasing once you increase the k. Okay, so how will this test error look like, or how will this validation error? We don't want to see the test error, because test error is the actual generalization that we want to do. So if you see this validation, so if you put k is equal to 1, validation will be really bad. So you'll get like because here it is, if you start k is equal to 1, I told you that at k is equal to, we have something called as overfitting. Yes, overfitting, because it's trying to capture everything. So it will be the error of validation will be really bad. It will be something like this, something of this sort. Okay, once you increase the k, you will find some optimal k at some point where you will get good validation. Well, you get this is validation error. Is this graph clear? So what I'm saying is, when k is equal to 1, I said this is overfitting. So you see that error is 0 over here, nearly 0. Okay, when k is equal to 1. So then on increasing k, when k became equal to n, the error basically was, it was not doing anything at all. Okay, everything was looking like an error. Then I said, when we have validation, so for validation k is equal to 1, it will really perform bad, because we are capturing a noise also. Okay, then slowly it will, when once you increase the k, at some point, like it may be go like this and this, but I'm showing you a smooth graph. Okay, at some point it will get the error really less, it will get really less error. Let's suppose that will is somewhere here, and then it'll the error will again increase after you increase certain k, and error will also increase. So if you now see this at this point, if you see some point over here, so for example, at this point there is some error, and at this point there is some error. This k is probably optimal, or we'll take average wherever the average error is less, so we'll take that. So if you see this portion, so this is one portion, and we have this, where we have this underfitting. Okay, when to call now the model is overfit or model is underfit? So if you see these two things, so we'll call, so when is the underfitting happening? So underfitting will happen if the training error is really high. Okay, so when will underfit when do we find this underfitting? So when do we find this underfitting? So if the training error, if you see this training error, it's really high, because it's not doing anything. Okay, and the test error and the course validation error is also high. If training error is very high, and validation or cross validation error is also very high, that means that our model is not basically doing anything, it is giving some answer. Why do we say it is overfitting? Overfitting, will say overfitting happens here in this portion. In this portion we got underfitting. So this is, let me make it with green, purple maybe. So this portion, if you see here, we have high training error and we have high cross validation error also. So this portion is underfitting. Okay, and if you see this red portion, here we have really less training error but very high validation error, so we'll say this is overfitting, because it's performing really good on the training set, but when brought into the actual real world, it performs really terrible. So that says that it was overfitting the model. Actually, it was capturing every noise, but when it was given the real world, it did not perform good. Okay, so when does overfitting happen? If training error is very low, if training error is very low, or error is low, and cross validation error, or validation error, we'll call it, validation error is high, this time we'll overfit it. Okay, then what is the best model? And this is some sort of best, like this region is good. If you see this region, well, like we'll take average, and average is less. Okay, here if you take the average will be really high. If you here again take the average will be also really high, because both of these values are high. So here one value is also high, one value is really low. When we average them out, still we'll get a value like this. Okay, so did you now see how to compute this? So because now we'll be computing the training accuracy, we'll be computing training error or accuracy, validation accuracy, and based on this, we'll be, based on these two things, we'll be computing our optimal k, we'll be computing our best fit. Okay, so if the training error is really high, or and cross validation error is really high, we'll say this model is underfitting, it's not doing anything. Overfitting means if the training error is very low, at training data it's performing really good, but when given the validation set, it is performing really poor, so we'll say it overfitted the model. Okay, and we just want to ignore these two things, and we want to get the results in between. That's, we say that average should be sort of okay, average of if you take average of this training accuracy and validation accuracy, that should be minimum. Okay, so if you see over here, average will be less than all other. Here the average will be way more, here the average will be again more, and if you see here, average will be some sort of optimal value. Okay, if I go to the code window, I have also coded this so that you get this into your head. Okay, I hope the screen is visible. Now here again, if you see that k is ranging from 1 to 10, Number of folds, I'm using 5 folds, cross validation. And now I have training errors and cross validation errors. Okay, I'm computing the errors in the similar fashion as I did previously. I'm just computing this training error as 1 minus accuracy, and cross validation error, if you see, 1 minus accuracy score of on this validation. Okay, then I'm appending over this training errors and this cross validation error. Then I'll plot a graph. If you see, the graph is over here. This is the graph. So initially, if you saw the graph over here, you see that at k is equal to 1, we have 0, at literally 0 error. Why? Because everything was overfitted. So here you see this, on this cross validation, it was performing terrible. Okay, that's why on this we call this this region, which I said this region will be overfitted region, because we are trying to we're overfitting, we are capturing everything. Again, if you see like this, on this data set, on this particular example, we sort of got some stable results over here. Then again it started increasing. Maybe this will again start, for example, increase something like this. Both of these will increase. So if you now see, if I compute the average of these, so if I compute the average of these errors, you see that the best value for k was in both was 1. I think here, if you see it, the best value of k using both of these was, let's suppose, 1, and the test accuracy was 0.84, and the test error was this much. Okay, this is how I captured the k. These are just on different. You might get confused that sometimes we're getting k is equal 5, k is equal 1, because I'm generating data randomly. The whole point was to get the point through. The point was here that based on this test error and based on the cross validation error, we're trying to try to find the optimal k. Okay, I think I might have coded even that average function also, so that I'll also like to show. I think that's not there somewhere. So maybe, I think you understood this point. Okay, so now you will sort of plot the training accuracy, and you will sort of plot a training error. You will plot the test or validation, we call them, and you will plot these two things. You will plot validation error, and you will plot train error, and based on that, you will say what is the optimal k, or what the optimal hyperparameters, parameters, not just k in this k and n. So but when you are doing some other hyperparameter tuning, you will see where to stop. I think, for example, graph will look something like this. So you'll see, if you increase graph will look something. This is our training error. Let's suppose training error kept on increasing and then slowly it decreased like this. Let's suppose this is our validation error. So validation error will be really high first. So it'll sort of increase, decrease somewhere like this, and then you will see where is the optimal way, which is the optimal. Let's suppose you will say here, this is the area where it will overfit. This maybe will underfit, and maybe somewhere around here is a good value of k that you set, and that you'll set for the hyperparameters. Usually in deep learning models, you will use it a lot. You'll use these two graphs a lot. You will see where is this accuracy, where is that validation error, where is this training error, and what values should we use, so that we optimally we make a model really optimal. Okay, is the concept of underfitting, overfitting, how to set this k really clear? Is it clear?
Yes, sir.
Okay, just mentioning some of these different splits again. So I'll mention what are the different split methods, and some advantages that they provide. I told you we'll discuss this in detail, and maybe we'll discuss maybe for a couple of minutes, so that you know that these things exist and what is the advantage, disadvantage of these things, so that you know how to split the data properly and how to evaluate these models properly. So as we saw, that the first split that we saw is just we split it into test and test and train. Then we saw cross validation. Then we saw k-fold cross validation. There is something called as stratified k-fold cross validation. Stratified k-fold cross validation. The first thing is, why is it required? It actually solves that problem if we have a really less number of data points. Okay, so sometimes if you have imbalance in the data, by less points I mean, for example, you have a really high imbalance in the data. Imbalance means, let's suppose we have class 1 and class 0, and in the here we have, let's suppose, 10,000 points. So in this class we have only 20 points. There is a high imbalance in the data. Okay, most of the times. So what happens is, in this imbalance data set, so model gets biased towards the class 1, because it sees more the data from class 1. So that's why it adjusts its parameters so that it gets the class 1 accurately. That's how we sometimes use this stratified k-fold cross validation. So what is this? So let me first tell how did the splitting happen. It's like variant of this k-fold cross validation. That's why I want to introduce you these things, because now you understood k-fold cross validation. You just will need maybe 2-3 minutes. Just give me 2-3 minutes, and I promise you guys will understand this. So how do we split this? Again, the same thing. The data set is divided into k subsets. The first thing is, this is normal everywhere. So retest will keep it separately. We don't even talk about this, because that's the unseen data for us. So retrain will split it into k folds. Okay, So when we split this into k folds, okay, so then what we do is we preserve the proportion of samples. So in each fold, so for example, if we have now, let's suppose we have 200 points, okay, and 200 points. In the 200 points, let's suppose we have one, let's suppose 190 points are from class 1 and 10 points are from class 0. Class 0, okay. Now when we use this fold, so what do we ensure is we sure the ratio remains the same, okay. So ratio here is 19:1. So what we'll do is we'll have 20 points here. We'll, let's suppose, have 10 fold, we'll have 10 folds. So in 10 folds we'll try to keep in each fold 19 points of class 1, okay, 19 points of class 1 and 1 point from class 0. Now total 20 points in one fold. So we have 10 such folds, so there will be in total we'll have 10 folds, okay. So we want to keep the ratio same. So if you see the ratio over here, so ratio over here is not in this, so ratio over here is 190 is to 10, that is 19 is to 1. So that's what I kept. If I have 10 folds, I'll keep this ratio constant. That is how do we split data. So this ensures the data in each fold is a representative of the overall distribution, okay. This ensures that. So because now you are training on 190 is to 10, so it is better to have this in each fold. Otherwise what will happen is sometimes if you split it randomly or something, so what will happen is here all the points will be from class 1, because majority of class 1 points. So sometimes here there will be 2 points from class 1 and 18 points from class class 1 18 points and class 0 2 points. So again sometimes what will happen, this will have class 1 points only, something like this. So in order to even this distribution out, in order to respect whatever the distribution there was in the total data set, so we'll do this k fold cross the stratified k fold cross validation, okay. So what is the advantage? Advantage is that it ensures that each fold is a representative. I'll write the advantage. So advantage is it ensures each fold has the representative, or each fold is representative, basically is representative of overall class data, of overall class distribution, okay. So if you have two classes, you'll do it by this, and it basically reduces the bias, okay. And this is particularly useful for the classification while there is an imbalance in the class distribution, okay. So this is called as stratified k fold cross validation, okay. Then we have some other ways of splitting also. We have something called as leave one out cross validation. So there is something called as LOOCV. This is called as leave one out cross validation. Leave one out, then cross validation. This is again the like whatever we have k fold like that. So but in here each fold will have a single data point. How do we split? So each fold will have only one data point, only one sample, okay. Each fold will have one sample, and then this process is repeated for each data point in dataset, resulting in n iterations, okay, where n is number of data points. So for each data point, so a single data point is held as a validation set and the remaining are used for training, okay. For first, like suppose we have n samples, so one sample will be set as validation and the rest of these points will be used as test and training. So why is it good? Why is it really good? Then this process will be reiterated n times if we have n points. So what I'm saying is only for this patient's data, where we had only 10 patients, okay, and each the test costed us $2,000. So we cannot even afford to bring more data points because where scarce data is very less. So what we will do is each will have this fold will have one patient. So we'll say first we'll have patient 1, patient 2, patient 3 till patient 10. So what we'll do is in the first iteration patient 1 will be validation and whole of these points will be our training, and then we'll test on this patient 1. And the second iteration what we'll do is we'll use this patient 2 as training and rest of these patient 2 as validation and rest of these as training, and we'll do for each 10 points like this. So this ensures that we are not biased towards anything, or if there is less data we can still make use of this technique so that we'll train our models. So if we have sometimes, like in the real world, there are scenarios like this, particularly in medical, where the test cost is very high, or something. For example, you are seeing you are capturing data and that event is very rare. For example, astronomical data. So let's suppose you are watching the stars and galaxies, and sometimes an event happens once in 100 years. So it happens once in 100 years. Now you know that how many data points will you have? You will have hardly, let's suppose, 15 to 20 data points of that. And if you want to train a model based on this only 15 to 20 data points, and then you can use this, what is called as leave one out cross validation. You will just leave one out as a validation, and for the rest points you will use it training and then evaluate the model again. Do the same for all the points. So this is called as leave one out cross validation. So this again can be computationally very expensive, okay, and it may lead to high variance models, what we call. So it has advantages. What are advantages? So advantages are that it utilizes all the available data whatever we have. For example, 10 data points, we'll use all of these points. So high utilization of data. And the other point that we have is it provides an unbiased estimate. Again, it gives unbiased estimate. Unbiased estimate. And why is it good? Actually, for the small data sets, if we have really small data set, it really is helpful. So what are disadvantages? So disadvantages are that it is very heavy, computationally expensive. Okay, these are some techniques. I think there was a question this year asked on DA on this leave one out cross validation. Are these splitting techniques clear? So whatever split we had so far, so there was a particular way in which we split the data. We were saying we'll take how many number of like in training data, we'll take this and we'll make the folds out of this. But now it boils down to two things. How do we split? Is there a criteria for splitting? Okay, will I take these particular points in my, because we haven't talked about which points will get into training, which points will get into testing, that we haven't seen. Okay, which points, or maybe I'll answer how points are selected, how the points, maybe data points are selected. That's the question. So far we have seen how to split. We have seen we can split in retrain, retest, and then in the retrain we can have this cross-fold validation. But which point will go into which set? That's the question. Okay. Now we have two types of main splitting over here. One is called as random split. Random split. So what is this random split? We'll split randomly. We will not care about anything. So whatever the point we have, we'll randomly either have it in first class. It has 50% chances. So if we have to split it into class 1 or class 0, any point, so any point will have 50% chances. So if we have a data point like this and some data points are like this, so each of these points, so this point will have 50% chance of going here or going here. Similarly, this point will have 50% chance of going here or here. So random splitting is this. So we are randomly picking up these things. So how will be the distribution of random? Let's suppose if we have 2-3 classes, we have one class like this. This is our class. Let's suppose one class of data points. Or we have other class like this. Now we have sort of, we want to say which point will go into train, which point will go into cross validation, which point will go into test, and something like this. Let's suppose this represents training, and this represents cross validation, and this represents testing. Okay, so how will the distribution? So some points will be like training. So point, this will be like training, in training, this will go into training. Okay, and some will go into this. This is our training. I'll write it. This is our training, and this is our cross validation, and then this is our testing. Okay, this is our testing. So here if you see it, so here some points will go like this. Okay, and other points, let's suppose, will be testing points. And similarly will happen for this class. So what I'm saying is random, there is a random split. So if I have to say it in a verbal sense, I'm saying if, let's suppose, this is our positive class and this is our negative class. So I'm saying if in a particular region, if there are high positive class points, so if there are very high number of positive points in D train, let's suppose, similar thing will happen with D test and D validation. D test will have again the high number of points in that region, and D cross validation will have the similar number, very high number of points. So basically what in the random, what I would trying to do is we're trying to randomly give the points. It's not like D train will have more number of points in a particular region and D test will have, for example, if we are capturing, giving the ratio of 60 20 20. So if we have, let's suppose, 100 points over here, so 100 points in this region, so 60 points will be in D train and 20 points will be in D test and 20 points will be in D cross validation. So what I'm saying is the distribution basically is captured, is basically actually correct. So whatever the distribution you are trying to capture is, by randomly you are doing that, you are ensuring that when I am capturing these things, I capture the right distribution. So samples should represent the distribution. Samples, they should represent the distribution. That's why we randomly split. We do not want to bias any on any terms. Okay, that's what this random splitting does. It will, for each point there is a chance it can go to test or it can go to train. Or in this case, if we are splitting like exactly like this, so there is the chance it will go 60% times here into retrain, 20% times into retest, and 20% times into cross validation. It depends how do we actually are splitting the data, and based on that it will have probability of going there. Okay, if I want to show you this into the code, maybe it will be a clear bit if I show it this into the code. I think I have written something. It should be visible though. I don't know if it is visible. I hope it is there. Yes. So here it is. So here I have actually made 3 clusters. If you see over here, so we have this cluster 1, which is a blue cluster, and then we have this red cluster, cluster 3, then we have this green cluster. Now if you see this, there is total green means training, so there are these training points, the distribution, the training. Then you see this cluster 1, which is like a little bit pinkish, it has outline of pinkish, so you see some points from this validation. Then these light colored blue, they are from the test. So if you see, that's like the distribution is purely represented like this. Okay, similarly in the here, so what I mean by showing you this is, so if in a particular area, if there are really high data points of training somewhere, so there will be high data points of testing again there. In that region there will be high data points of cross validation again there. So similarly in this, if you see these 2 clusters, same happens with this is what is meaning of the random splitting. So we'll give the probability in terms of how in terms of ratio that we are splitting the data into. That's what I told you in the theory also. So again we are respecting the ratio. If we have d train hyphen d test, and then we have d cross validation. Let's suppose in this, if the ratio of the points of class 1 to class 0 is 1 is to 2, in the d test it's again 1 is to 2, and nearly approximately equal to 1 is to 2. Here it will be again 1 is to 2. So that is the whole training data, whatever it is representative of, we try to capture the whole distribution into this d test and d cross validation. That's the point of random splitting, if you want to randomly split. But sometimes this random splitting is not good. Okay, let's suppose in this emails, so in terms of emails, so what will happen in terms of emails? So if you have some data, so I'll make this is our data, this is our data matrix. We have this xi transpose, this is each of our emails, and then we have corresponding labels. So if we split the data, but you know these attackers, they can come up with different ways, or these spammers, they can come up with different ways to create new spam mails. Okay, so what we have to do is, if for example I had, let's suppose x1 x2 x3 x4, let's suppose x 100 emails. So if I try to randomly try to split them into d10 and d test. Okay, so what I'll do is, if I got some x1 x100 x54 something like this, I got into d-train. So when I trained them and I got some into validation, x59 x64 x81, and so on, into our d cross validation. Then in the testing I had some, basically random splitting. So what I'm saying is that attackers usually they change their ways of creating, or the spammer they change their ways of writing the mails, so that we cannot capture. So here in the training it is a distribution. So when, let's suppose we train the model on this cross validation, we got 80% accuracy, let's say. In the future what will happen, there will be a mail. Okay, we expect that there will be high accuracy, but as you know, the spammers, they constantly change their ways of attacking this, so we may not capture that. So what we'll do is, we'll probably get a really bad accuracy, we'll get some 10% accuracy over here, because maybe in this distribution, retrain and cross validation, no such email was found, because now spammers, they sort of changed all of their ways. So sometimes maybe if we get 100%, if you get 100% accurate, this is also a terrible thing. Why? Because the problem may be, whatever mails are coming, they're also in here, so there is a replica of mails. Okay, one spammer is sending multiple mails. So the better thing is that we'll do time based splitting. We'll do time based splitting. So what is the meaning of this time based splitting? Because now we'll have a time column in these emails. Okay, we'll have these emails written and we'll have time corresponding to them. Okay, this will be time column. So what we'll do, we'll sort based on time, sort emails based on time. So when we do this, so now if we have now sorted emails based on time, let's suppose this is our data set now. Say this is our email 1, email 2, email 3, like this is our data. Okay, sorted on time. So I'll use, for example, this is my today. So I'm right here. So I'll say today, this whole data is this point right here. This is today minus 90 days. So this whole data is for 90 days. So I'm using for today minus 90 days, let's call this as my whole D train, and now I'll have to split the D train. So I'll say today, this point, today minus, let's say 15 days. Okay, I'll make it a better diagram. So this is my total data that I have. For example, in the timeline, I'm right here. This is my today. This is future. So this is today. This is what is coming, and this is what is my past. So what I'm saying is, this is my first line. So I'll say this is today minus 15. Today minus 15 days. Okay, and this right over here is today minus 90 days. So I'll say I'll train on this. Okay, I'll cross validate on this, and then I'll test on future. This makes sense if you are a let's suppose machine learning engineer in working in Google, and you have some emails, or maybe for example in Amazon, and if these are reviews, so you will train on previous reviews and you will cross validate again on some previous reviews, and for the future reviews you will test them. If if it was performing terribly, that means that you have to update the model, and you will keep on updating the model. Sometimes time based splitting makes sense if there is a time column, and you should split based on time. In the stock market also, so in the stock market, because we have time series data, so that time the splitting based on time is sort of preferable. Why? Because there is a temporal component in that. For example, if you want to create a model and you want to predict a stock, which I think I'll show you how, what are different statistical and what are deep learning models which are used. Let's suppose stock is going like this, something like this. So it is better you use this much of data, let's suppose, into D-train, and this much of data into cross validation, and in the future, let's suppose this is our future that we have to predict. Okay, this we'll use, and this thing is called actually back testing. Okay, we make some strategy, and then we see how it happened, what was for example, if I train my model onto this, and when I'm testing the model, this should actually be kept as validation, and then I'll predict for the future, and here we call it back testing. I just show my model data like this data. Okay, I showed it today. This is my today, and this is my today minus 15. This is my today minus 90. This data I trained my model on, and then I validated on this model, on this data, and at the end I have to predict the future. This is time based splitting. So when you are having this time series data, or when you are having, for example, emails, reviews, and these things where there's a time component is really important, where you can have attackers, a spammer, they change their ways. So it is better to do the time based splitting, and random splitting is preferable there, while the distribution is some sort of similar. It does not change a lot. The distribution remains same. For example, humans, distribution remains same, so you can do the splitting randomly. For example, if you collect let's suppose some patient data of in a region, so maybe if that disease is sort of having a particular distribution and it does not change over time, so maybe you can do the random splitting. Is the random splitting and this time based splitting clear? Where we do random splitting, where to do this time based splitting, is it clear?
Yes, sir.
Yes,
So
sir.
here we have understood a lot of concepts about overfitting, underfitting, how to choose these parameters, okay, how to split the data, and there's a lot of concepts that you have to digest a bit, because all these concepts, most of them will be again reused everywhere, and we'll maybe come back to these concepts. Sometimes we'll just brush them up. So it's a really important lecture, because most of the models, I'll say most, because some models may not use, so most of the models and most of the times I'll refer to these things. I'll say, now this is my training set, this is my testing set, this is my validation set. Here I am using cross-fold validation, here I am using time-based splitting, maybe in some model I'm using random splitting, and you must know most of these terms that time. And we'll maybe if you forget some term, I'll brush that things up then. That's the reason I just introduced you to KNN first, and then I wanted to basically introduce these all terminologies. Now you know the KNN algorithm, and in the next session what I'll do is I'll tell you different versions of KNN, different versions of KNN. If you remember, in the previous previous to previous session, we read about KNN, and in that KNN, the problem was that this was very time taking, time consuming, and space consuming. I think the complexity was order ND for both time complex and space complexity. Now we'll see if there are ways to reduce this time complexity. There is something called as KD trees, which we will study, okay, and there is something called as LSH, okay, and these two techniques we'll use, and we'll implement this KNN, and we'll make it a little bit better in terms of complexity, so that this can be deployable. If you want to make this model deployable, we'll use that, and these are different versions of this KNN, okay, and this will also give an introduction to data structures. I'll just stop the recording here. If you have any questions, I'm willing to take that.